Hello, and this will be a very interesting video to you guys, particularly if you're sort of your math method stuff. And what we're doing here is looking at the second derivative. Second derivative, I'll just put that, but what we're going to use that for is to help with curve sketching. You would have learnt in math methods that if you've got some function y is equal to f of x, then if you find the derivative of y, in other words f dashed of x, if you find that, and then wherever that's equal to 0, that you would have been told that will tell you it will be a stationary point. So there'll be some stationary point, and what that means is that on some graph like that, if you solve f dashed of x is equal to 0, it will tell you what this point is and what this point is, which is very, very useful when you're trying to sketch a curve or trying to solve a problem where you want to know where the minimum and maximum values are. Okay, really handy. What this doesn't tell you is, what's happening to the curve, before it, or what's happening to the curve in between here. We don't know what's happening in here to the curve. And these are really important questions too. Where is, if we're not interested in the maximum minimum, but we're interested to know, well, where is the curve the steepest or something like that? These are questions that can't be answered by this. The things that help us a lot more than this is very, very helpful. What's even, which adds to the value of it, is finding the second derivative. And if you think about that, and we write that as f double dashed of x, it's the second derivative. So if you have y is equal to, let's just say x to the power 5, then your derivative dy by dx, sorry, that's really messy, is 5x to the power 4. And your second derivative, which you can either write that as f double dashed, or if you're using Leibniz notation, is d squared y on dx squared. If you're the next derivative, 4 times 5, so it's 20x cubed. So that's your second derivative. You can also write that as f double dash of x is 20x cubed. So we're just taking the derivative again. Now if you think about what does this mean, remember, dy by dx tells you the gradient. Okay? In other words, it's the change in y over the change change in x. Okay? That's what dy by dx means. So, what does the next derivative, what we're looking at now is the derivative of dy by dx. What that means is the change of gradient with respect to x. In other words, how is the gradient changing? And so if you think about that, and we draw another graph, what is happening to the graph? And I'll draw a similar sort of graph like that. What is happening to the graph here? And I'll just go a red pen and have a look at this. In other words, what's happening to the gradient here? Well, here, the gradient's really steep here, but it's getting less and less and less. Can you see how it's getting smaller in time? It's really steep, but it's getting less steep as it goes up to here. So here, the second derivative, I'll just write that, the second derivative will be less than 0. In other words, it's getting smaller. It's getting smaller and smaller and smaller. It gets to this point here, and it turns around. What's happening to the second derivative in this sort of area here? Well, it's at 0 here, the gradient is 0 there, but it's becoming a negative gradient in here, so it's getting negative and negative and negative. I'll just go up to here, okay? And it's becoming smaller and smaller in there. So in this little section here, it's still less than 0. And in fact, this whole section here, between here and here, it's getting less than 0, it's getting smaller and smaller. It's positive here, so it might be 2 there, and 1 there, and half there. It hits 0 there, the gradient, and then it starts going, so it might be negative half, and then negative 2, and it gets to this point. Now it gets to this point and stops changing. And then it stops changing and then starts getting bigger. Here you've got a large negative slope, but it starts getting bigger and bigger and bigger, and it works its way up to 0. So there's 0 again. Your gradient's equal to 0. The gradient's getting bigger there. So here, f, I should draw this in a bigger diagram. F is bigger than 0. Okay. So the gradient is getting bigger. The gradient is growing and growing and growing, and then it hits 0 again. I should draw this on a bigger diagram. Never mind. Do it in class. And so what's important here is that f double, and it's getting bigger and bigger and bigger up until some point here. And it's growing and growing, getting bigger and bigger, and then it stops growing and then goes back the other way again. It's going less and less and less. It's quite positive here, less positive, hits 0, and then it gets smaller and smaller and smaller. It's going in the negative direction. I don't know whether I've drawn that. We'll not worry about that because I don't know what I mean there. So the important points here are where it where it stops growing in one direction and goes in the other direction. Here it's getting bigger and bigger and bigger and bigger and bigger. It stops changing and then starts getting smaller and smaller again. And at those points, that point and that point, we call those points of inflection. And those points is where there is no change in the gradient at that point. And so f double dash of x is equal to 0 at those points of inflection. It stops changing and starts going back in the other way. Instead of growing bigger and bigger and bigger there, it stops changing and goes back in the other direction. And so that's really important to understand. And these points here are actually the steepest points on the gradient. Okay, so if you're looking for where is the steepest point in the graph, you actually get those points of inflection. That's where this graph will be at its most steep. Okay, let's just, I might do one quick example and go into some more technical examples in the next video so that I've not got enough time. Okay, so let's just have a look at a graph. So an example, how this helps with curve sketching. So let's just look at y equals x to the power 4 minus 6x squared plus 4. Okay, if we want to sketch this thing, that's quite a difficult function to sketch. So let's just have a look at it. What's the first derivative? First derivative, 4x cubed minus 12x. That's our derivative. I'll just take out 4x from that and we'll be left with x squared minus 3. And if we set that equal to 0, we get x is equal to 0 or x is equal to plus or minus root 3. Okay, so this means, what does this mean? We will get stationary points at x equals 0 and x equals plus or minus 3. Okay, so this is going to be just a really rough sketch. Okay, so I'll just do this. So we're going to add x equals 0 and I'll just put root 3 here and negative root 3 there. Okay, so we're going to get something. At this stage, should we find out what the coordinates of those are? Sure, let's do that. If x equals 0, then y is equal to 0 and minus 0 is going to be 4. So we're going to have some point 4 up here where you're going to have either a maximum or minimum. Root 3, I shouldn't have done this question. Root 3 squared is 3, that's 9 minus 18, so that's negative 9 plus 4 is negative 5. So you're going to have some points down here at negative 5, and it should be the same for that. Yes, it will be, thank goodness. Okay. So we've got some some stationary points there. Now, let's find the second derivative. I was going to do it another way, but let's find the second derivative. Okay, d squared y over dx squared. Second derivative, you just take the derivative again. 3 times 4, so that's 12x squared minus 12. Where is that equal to 0? If that's equal to 0, implies we'll just take out 12 and we get x squared minus 1 equals 0. Therefore, this is really messy. I've set this out really bad because I put the graph right in the middle, which is a bit stupid. X is equal to plus or minus 1. And so what this means, that at x equals plus or minus 1, you get the second derivative equal to 0. And that means that the gradient stops changing when at the points x equals plus or minus 1. So they will be points of inflection. Now I've set this out really badly. Don't copy this setting out. I'll do it better in class, I promise. So at x equals 1, so root 3, I'll just put it about there. There's 1, and there's negative 1. Really messy. Sorry about that. So what's the y values when x is equal to 1? We get, when x is equal to 1, we get 1 minus 6. So negative 5 plus 4 is negative 1. So somewhere down here, we're going to get a point of inflection. Same for there, you get the same value because it's just even powers. So we get those sorts of things. And so we can instantly tell what's going to happen. The graph must look something like there. We're going to get a minimum. That comes up. That's really badly drawn. It's hard on the tablet that I've got. I apologise. And it goes a minimum. Sorry, it'll be like that. So it'll go up something like that. And so these help us. So can you see here? The stationary points were found using the first derivative. Okay, they're nice. So they're very helpful to this curve sketching. What's not even more helpful, but which is of more help, is to also find our stationary points there, and that's where the curve stops getting bigger and bigger and starts turning around. And it starts going back in the other direction. Okay, so instead of getting steeper and steeper and steeper like that, it gets steeper and steeper. It stops and it turns around like that, and you get this point of inflection there rather than that. Okay, that's what's happening there, and that's very, very helpful. The other area that's helpful is to look at these. If you look at these stationary points here, and you want to know, are they a minimum or a maximum before you even sketch it. On this one, it was kind of obvious as which one's a maximum, because it would be impossible for this one to be a minimum, because you can't turn around back down there. It doesn't make sense. But what you could do is you could say when x is equal to 0, okay, when x is equal to 0, what's the second derivative equal to? Okay, so our second derivative was 12x squared minus 12. So that would be 12 times 0 minus 12, which is equal to negative 12. Okay, so the second derivative, when x is equal to 0, the second derivative is equal to negative 12. What that means is that the gradient's getting smaller and smaller and smaller. In other words, it's big, it's getting less, it hits 0, it gets a little bit smaller, 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 smaller. And so what you get is a maximum, a local maximum. And in general, if the second derivative is less than 0, you get a maximum. If the second derivative is greater than 0, you get a minimum. If the second derivative is equal to 0, you get a point of inflection. Okay, so this is how it helps with curve sketching. So that was just a really rough example. In the next video, I'll do a cleaner example. And I'll set it out all nicely, and I'll even put a little graph in there and stuff like that. Okay, so next video.